New images captured by the James Webb Space Telescope have surprised researchers rather than broadened our understanding of the universe. These images revealed a disturbing fact. Our current physical understanding is not sufficient to explain the nature of the cosmos in its early stages, where the Big Bang theory reaches its limits. This forces us to consider new hypotheses about its origin. The question arises as to how the universe was formed in detail and why this new discovery challenges even the most experienced astronomers. Find out with us more about the Big Bang and the revolutionary details of the discovery. Before we get into the details, let's recall for a moment the concept of the Big Bang, which is often mentioned to describe the creation of the universe. Contrary to common belief and some misreinterpretations, the Big Bang was not an explosion in a pre-existent space. Rather, it was space itself that originated approximately 13.8 billion years ago, along with matter and time, from an original singularity. To clarify in simpler terms, in the field of physics, in astronomy, singularity is a term used to describe places where gravity is so intense that the curvature of space-time becomes infinite. But how can we be so sure about all this? Today, after billions of years since the beginning of the universe, we find that our cosmic home is formed as a part of a fundamental process. For experts, this represents an intrinsic feature of the universe since its very existence, its seemingly endless expansion. However, it is crucial to understand that the cosmos is not expanding into a pre-existent space, but that space itself is constantly increasing in size. If we follow conventional theories, it is estimated that the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age, when the first luminous celestial objects clustered together to form mature galaxies. However, how fast these galaxies grew is still an unsolved enigma. An important clue to solving this galactic enigma emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected a number of galaxies, some of which had already existed some 300 million years after the formation of the universe. However, compared to the galactic structures that developed in the millions of years later, these early galaxies remained considerably smaller and less massive. This fits perfectly with the scientific model accepted by researchers. The density of matter in the young universe was simply not sufficient to give rise to galaxies of the size of the galaxies we observed today. What began as a discovery of 6 bright redshift luminous spots apart from James Webb turned out to trigger one of the most significant astronomical crises of recent times. Now, although these newly discovered galaxies are similar in age to previous record-holding galaxies, they are almost as massive as our own Milky Way galaxy. This has had an intriguing mystery through astronomical research thanks to a team from Swinburne University of Technology in Melbourne. After examining a series of images captured by the NIRCam near-infrared camera, the experts finally identified the previously mentioned light sources. Using redshift, the scientists calculated that the light from these objects took more than 13 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had already existed between 500 and 700 million years after the alleged Big Bang. By analyzing the characteristics of these structures, it was concluded that the Webb telescope had captured 6 extremely early galaxies in the image. Surprisingly, these galaxies were so massive that they defied conventional expectations of cosmology. Instead of finding the expected dwarf galaxies, structures are identified that they were almost as massive as our own Milky Way galaxy, despite having formed at an early epoch. If we continue to analyze the data collected by the James Webb Telescope, this gravitational-bound grouping of stars were already more than 10 billion times the mass of the Sun at that time, and one of them may even have surpassed the 10 billion solar mass mark. However, even if this possibility is considered, the mystery is still not completely solved. Even in this scenario, there would be significantly more stellar mass in the early universe than previously assumed. This poses a puzzle, since shortly after the Big Bang, there was not enough normal matter available to form so many stars in such a short period of time. The detected objects contradict virtually all conventional cosmological theories. Even if only one of these galaxies turns out to be genuine, it will go beyond the limits of our previous assumptions to explain the existence of these structures. Furthermore, the density of matter in the early cosmos would have to have been up to 5 times greater than previously assumed in order to explain this phenomenon. Another equally mysterious explanation is based on the fact that these galaxies developed in a way that is still completely unknown to us. These discoveries and the debate surrounding the Big Bang are leading more researchers to move away from this theory. Many astronomers with more alternative views are frustrated that they are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as unfounded eccentrics. However, it is undeniable that even experts who still defend the Big Bang theory are constantly faced with questions without clear answers. These questions include particular issues, such as why and how 13.8 billion years ago. Did something literally come out of nothing? Can something really originate from nothing, or was there something triggering event? Or was it just all a coincidence? Stephen Hawking pointed out that the concept of time as we know began only with the Big Bang. Therefore, this process could not have been triggered by something else or someone external. A similar controversial question relates to the uniformity of radiation and density throughout the cosmos. No matter in which directions or at what distance we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Conservative scientists explain this theory by the theory of cosmic inflation. However, other experts take this assumption and take it a step further with the theory of chaotic inflation. According to this idea, it is possible that this process has stopped only in some regions, like bubbles, and continues infinitely elsewhere. This implies that multiple universes form in these bubbles, each with its own individual physical laws. Considering this context, a fundamental question arises. What if the cosmos does not represent the complete whole, and even more, if another universe existed before ours? In that case, the Big Bang would become a great cycle. Following this theory, words like beginning and end are ambiguous concepts in a cosmic context. What we usually refer to as the Big Bang could have been simply a transition in a continuing cycle. As soon as this universe exists, a new one emerges from it. According to this perspective, our universe is part of a larger multidimensional structure. Within this model, the idea of an external cycle of collapse and rebirth of the universe is put forward. However, this is not the only perspective presented in the field of cosmology. Apart from the Big Bang theory, in 1955, for example, an article appeared in NASA's Cosmic Times arguing that there may have never been a Big Bang, since the universe has existed for an infinite time. In this view, the expansions of the cosmos would be non-existent, and the continuous formation of matter could give the impression of a constant expansion of the universe. Another intriguing, though controversial theory comes from the world of quantum physics and string theory. Supposedly, some experiments have suggested that the universe and everything in it does not actually exist. In simple terms, what we perceive as a visible universe could simply be a flat hologram projected onto a sphere. Therefore, there is the possibility that our reality is the result of a higher simulation. While this may sound like the plot of a fanciful science fiction movie, it can be connected to the Kardashev scale. The scale is used to measure the level of development of a civilization according to its ability to use energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire galaxy, it could have created a perfect simulation. However, finding out the truth in such a scenario is a very complicated matter. Do you still believe in the Big Bang theory, or do you consider alternative explanations more plausible? Throughout history, since ancient times, humans have gazed at the stars and pondered the vastness of the universe. Now, however, we can say that the enigma of what lies hidden in the corners of the universe has finally been revealed. The James Webb Space Telescope has unveiled a discovery that is making a profound impact on the field of astrophysics and leaving scientists amazed. This finding is so revolutionary that it could completely change our current understanding of the cosmos. So, what exactly has this advanced telescope at the far reaches of the universe revealed? Get ready for an out-of-the-world experience as we'll delve into this groundbreaking discovery and its implications for the future of science. If you're interested in keeping up to date with news from the universe and beyond, subscribe to our channel. Be sure to like this video and turn on the notification bell. Imagine having a time machine that would allow you to witness the origin of the universe. Well, The James Webb Space Telescope gives us the opportunity to travel billions of years into the past and observe the far reaches of the universe in more detail than ever before. With its state-of-the-art infrared detection technology, the James Webb works like a superhuman eye capable of perceiving objects and phenomena invisible to us. What's the result? Astronomers have captured stunning images and gained invaluable information about the workings of the universe as a whole. These stunning images show galaxies and clusters, including the distant and elusive MAC SO647GD, perplexing the scientific community. The image reveals an astonishing spectacle, a stunning array of galaxies glittering like jewels in the vast emptiness of space. However, what really excites scientists about this image is not only its beauty, but the enormous amount of information it provides. MAC SO647GD, a distant galaxy discovered a decade ago by the Hubble Space Telescope, has been studied in great detail thanks to the James Webb Space Telescope triple lensing effect, which seeks new insights into its structure, composition, and behavior. Scientists are especially fascinated by the question of whether MAC SO647GD is a single galaxy or two groups of stars within a galaxy, and hope the James Webb can provide them with an answer. But the James Webb discoveries do not end here. There is much more to discover and explore in the far corners of the universe. This cutting-edge telescope has opened the door to a new world of possibilities and is redefining our understanding of the vastness and complexity of the cosmos. The telescope has gone further, unveiling galaxies beyond our ability to imagine. And these are not just any galaxies, but some of the oldest galaxies in existence, such as Z12, which was captured just 350 million years after the Big Bang. Take a moment to take that in. This galaxy is more than 13 billion years old, and its discovery has revolutionized our previous understanding of the origins of the universe. Previously, the Hubble Space Telescope had observed the galaxy GNZ11, which existed just 400 million years after the Big Bang in 2016. However, thanks to the incredible capabilities of the James Webb, we have been able to see even further into the past, revealing galaxies that existed only 250 million years after the Big Bang. One striking example is the galaxy CEERS 93316, with an impressive redshift of 16.7. This is testimony to the unprecedented technological advances of the legendary James Webb Telescope. This galaxy is such an enormous distance that we are observing it in its early stage, and its discovery is part of the Cosmic Evolution Early Release Science Survey, which uses the James Webb to capture images of distant galaxies. Although spectroscopy is required to confirm its redshift, preliminary NIR-CHEM data have already ruled out the possibility that it is a low-mass star or an unobstructed active galactic nucleus. The discovery of CEERS 93316 adds to the growing body of evidence suggesting that galaxies formed even earlier than previously thought. The exciting thing about this finding is that it transports us to a time before the stars we know today existed. It is like finding a hidden treasure that takes us back to what is commonly known as the Dark Ages, a period when it is believed that the first galaxies in the universe began to take place. It's like having a time capsule that allows us to go back billions of years and get a unique glimpse of what our universe was like in its earliest days. The discovery of CEERS 93316 is just the beginning of what is possible. NASA has hinted that James Webb could detect galaxies at redshifts greater than 20, just 200 million years after the Big Bang. This means that the discovery of CEERS 93316 is even more significant, as it offers hope that these elusive galaxies may actually exist. It opens up a whole new world of possibilities about what we might discover in the vast expanse of the universe. In the farthest reaches of the universe lies another fascinating galaxy that has scientists abuzz with excitement, Abell 2744Y1. This galaxy lies at such a colossal distance that its light takes a staggering 13 billion years to reach Earth, making it practically as old as the universe itself. Despite this enormous distance, the Spitzer, Chandra, and Hubble telescope have managed to capture an image of this extraordinary galaxy, by working together to collect data from different wavelengths of light. They even used the phenomenon of gravitational lensing, predicted by Albert Einstein, to obtain an image of about 2744Y1. What is truly amazing about this galaxy is not only its age and remoteness, but also its incredible rates of star formation. Despite being only 50 times smaller than our own Milky Way, about 2744Y1 generates stars at a rate 10 times faster than our own galaxy. This accelerated rate of star production is typical of galaxies that existed in the early days of the early universe. This impressive rate of star formation has puzzled scientists and piqued our curiosity to discover what else this galaxy has in store for us. Although exploring this galaxy in depth is no simple task, the information gathered so far will keep scientists busy for many years to come. Have you ever pondered the vastness of the universe? It is so vast that our minds cannot fully comprehend it. Yet, despite its staggering magnitude, scientists have attempted to measure it, and what they have discovered is truly astonishing. The observable universe has a radius of approximately 46.1 billion light years, but there is much more out there that is beyond our ability to observe. Based on observations and our knowledge of physics, scientists have determined that the universe extends on a globally flat scale with a remarkable accuracy of 0.25%. However, there is a possibility that the universe is curved and forms a loop upon itself. In such a case, the observable part of the universe could be at least 23 trillion light-years across and contain more than 15 million times the volume of what we can currently see. These perspectives invite us to reflect on the immensity and infinite possibilities that the universe holds, prompting scientists to explore and discover more of its hidden secrets. Some scientists even hold the possibility that the observable universe is considerably larger than what we know so far. According to this perspective, it is conceivable that the event known as the Hot Big Bang simply marks the beginning of what we can observe, but not necessarily the origin of space and time itself. However, this notion raises even deeper questions about what we do not know about the universe. According to the theory of cosmic inflation, the universe experienced a period of rapid expansion before the Big Bang, in which new space was generated at an extraordinary rate. This idea raises a number of unanswered questions about the scale and very nature of our universe. For example, how large was the region of the universe subject to inflation? And is the hypothesis of eternal inflation, where the universe expands indefinitely into the future in certain regions, plausible? Also, how long did the inflation stage prior to the Hot Big Bang last? It is likely that the universe where inflation occurred was only slightly wider than what we can observe, or that evidence of its limits will emerge in the future. Despite all these uncertainties, it opens up the fascinating possibility that there are countless additional universes out there, similar to our own in terms of physical laws and structures. This conjecture tantalizingly suggests the existence of complex life forms on some of these worlds. It is amazing to consider that we are merely a tiny particle in the grand scheme of the universe, with vast territory to discover. One example of this galaxy is GNZ11, which has been observed as the most distant galaxy ever detected by humans. It is at an impressive 32 billion light-years away from our planet. This means that the light we are seeing today from GNZ11 began its journey to us when the universe was just 3% of its present today. The magnitude of this distance to GNZ11 is so colossal that it is difficult to comprehend. Moreover, if we take into account the expansions of space, the distance from Earth to GNZ11 extends to about 46 billion light-years, almost half the total age of the universe. What makes GNZ11 even more intriguing is that it marks the limit of our observational capabilities. It lies on the surface of the last scattering, the point where the first photons emerged after the recombination and decoupling of matter and radiation. In a way, GNZ11 represents the edge of the observable universe, beyond which can see and explore nothing. As we contemplate the vastness of space, it is natural to feel small and insignificant. The universe is so vast and infinite that it can overwhelm us. However, as we delve deeper into the cosmos,
we gain a better understanding of our place in it. By exploring the origins and evolution of the universe, we gain insight into the processes that have shaped it over billions of years. What is the age of our universe? This question has puzzled scientists for centuries. Although it seemed like a simple question, over time it has become apparent that finding the answer is not so simple. Today, this question continues to be debated as new research constantly challenges our understanding of the age of the billions of galaxies that make up our universe. A week ago, a groundbreaking study based on data from the James Webb Space Telescope challenged the widely accepted notion that our universe is approximately 13.8 billion years old. The study suggests that the universe could be twice as old, which would break the cosmological model and solve the enigmatic and complex problems of the first galaxies. But is this really possible? Join us on this journey because we are going to dive into the immensity of the cosmos to analyze this discovery. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video, share it so it reaches more people, and activate the notification bell. It is important to note that one of the most revealing facts about the universe is that we know its age, 13.8 billion years. However, this figure is being questioned and reevaluated based on exciting new research. If we were to go back in time, we would discover that the early universe was very different from how we know it now. The stars and galaxies we observe today arose through gravitational mergers of objects consisting of younger, pristine stars. In those initial moments, no stars or galaxies existed. If we continue to look into the past, we would arrive at the moment of the Big Bang, which marks the beginning of the universe as we know it today. Today, astronomers and astrophysicists studying the early universe claim to have estimated its age with an uncertainty of less than 1%. A remarkable achievement that represents the discovery of the universe's birthday. To measure the age of the universe, there are two methods compatible with this figure. The first is by tracing the history of the universe, a powerful way to estimate its age. This method is based on the discovery of the expansion of the universe in the 1920s. In physics, if you know the equations governing the system and you know how it evolves in time, you can go back into the past or forward into the future as long as the laws of physics and the content of the systems do not change. In the field of astrophysics and cosmology, the laws governing the expansion of the universe arise by solving the theory of general relativity for a universe that, on average, is filled with equal amount of stuff everywhere and in all directions. We call this homogeneous, equal everywhere, and isotropic, equal in all directions universe. The consequences of this resolution are known as the Fridman equations, after Alexander Fridman, who was the first to derive them 99 years ago in 1922. These equations tell us that a universe full of stuff must expand or contract in a particular way. The rate of expansion or contraction changes with time and depends only on two factors. First, the rate of expansion at any point in the present, and second, what kind of content the universe has at that specific point. In the early days of cosmology, they used to joke that cosmology was the search for two numbers, implying that if we could measure the expansion rate and how it changes with time, we will have the information we need. Currently, we know those two numbers, the Hubble parameter, which represents the current expansion rate of the universe, and the deceleration parameter, which is its negative, meaning that the universe is not slowing down as previously thought, but is accelerating its expansion. If we could accurately determine the expansion rate of the universe, we would be able to know in detail the composition of the universe. That is, we could know about the normal matter, dark matter, radiation, neutrinos, dark energy, and other components that are present.
We could also go back in time to the initial moments of the Big Bang, where the universe was very hot, dense, and occupied a small volume. The amount of time we take to go back to that point gives us the age of the universe. The study published in July 7th in the journal Monthly Notices of the Royal Astronomical Society appears to confirm that previously estimates of the age of the universe were significantly wrong. This new study addresses what is called the impossible problem of the first galaxies, which has long puzzled scientists. According to the study, some galaxies that were thought to have existed shortly after the Big Bang actually appear to be much older than previously estimated. Observations made with the James Webb Space Telescope showed that galaxies and stars like Methuselah appear to have a level of mass maturity normally associated with billions of years of evolution. This is surprising considering that it was believed that these galaxies formed hundreds of millions of years after the Big Bang. An assistant professor of physics at the University of Ottawa suggests that these puzzling observations can be explained by the fact that our universe is actually much older than previously thought. The professor's study presents a new model that extends the time of the galaxy formation by several billion years, giving the universe an age of 26.7 billion years, twice what is generally accepted. This model incorporates Fritz-Zwicky's tired light theory, which suggests that the observed redshift in the light from the distant galaxies is due to a gradual loss of energy over large cosmic distances. According to the tired light theory proposed by Zwicky, light becomes weaker or tired as it travels great distances through the cosmos. This idea contrasts with the current established theory, which holds that the redshift observed in objects such as galaxies is mainly due to their moving away from us as a result of the expansion of the universe in all directions. The tired light theory has generated significant controversy within the scientific community. Astronomers debated whether the loss of light energy over cosmic distances would not only cause a redshift, but also a decrease in the intensity and brightness of light. Critics argued that if this were true, distant objects could appear much dimmer than actually observed. Furthermore, this theory proposed by Zwicky in the mid-20th century conflicted with the discovery of the cosmic microwave background radiation, which is an uniform radiation present throughout the sky and represents the residual energy of the Big Bang. This radiation provided strong evidence in favor of the expanding universe theory. Although Zwicky's theory was initially found to be in conflict with observations, a new perspective is proposed that allows the tired light theory to coexist with the expanding universe model. According to this new interpretation, the redshift phenomenon can be viewed as a hybrid phenomenon that combines both the expansion of the universe and the gradual loss of energy of light during its cosmic journey. This new interpretation offers a credible explanation for the first observations of galaxies, in addition to considering the theory of tired light. It also introduces the concept of blocking constants, an idea proposed by physicist Paul Dirac. These locking constants are fundamental physical parameters that cause particles interactions, and it is suggested that they may have varied over time. By taking into account the evolution of these blocking constants, the proposed new model extends the time frame for the formation of the first galaxies observed through the James Webb Space Telescope. Instead of just a few 100 million years, this new time frame allows spanning several billion years of cosmic evolution, providing a satisfactory explanation for the development and mass of these ancient galaxies. This model also challenges the radiation interpretation of the cosmological constant, which represents the dark energy responsible for the accelerating expansion of the universe. Instead, a modified constant is proposed that takes into account the evolution of the constraining constants. This modification in the cosmological model may help solve the puzzling puzzle of the small size of galaxies observed in the early universe and provide a more accurate picture of cosmic evolution. What do you think? Do you think we've been wrong all this time? Let us know in the comments box. If you liked the video, remember to hit the like button and subscribe to the channel so you don't miss out on more content like this. Thank you very much for watching the video, and I'll see you in the next one around.